Greetings, peeps. An introduction to electrical circuits, but this time we're looking at schematic diagrams. So you got the intro before to circuit elements and the like, connecting them together. Now we're going to look at how we can model them. And so a schematic diagram just has various symbols that represent different electrical elements, and it's used by electrical engineers and physics peeps, the like, to be able to kind of document, just like a blueprint is for a house. These things represent electrical circuits in the abstract, and then they can be built in the laboratory or actually on, little circuit boards that we use in everyday practice. So your iPhone, for example, or Android would have a schematic diagram that would represent all of the other features. And so we're going to do a very, very basic one so you can be introduced to the core elements that we'll be using. So this is the entire circuit, and here is a voltage source, like perhaps a battery or maybe the power supplies that we've been using as well in the laboratory. So this is a voltage source, and a voltage source has two plates, one longer than the other, and the longer plate represents the positive side, the shorter plate, the negative side. So a voltage always has polarity, positive and negative. And so we'll see that that's the case in terms of how energy is used in the circuit. Voltage is energy per unit charge, and so this tells us something about the polarity of that voltage. The source supplies energy to charges in the circuit, this voltage source here. On the other side is something called a resistive element, or in this case, anything that consumes energy or transforms it into another form. A resistive element could be simply a resistor that converts the electrical energy into something like heat. It could be a bulb that converts it into light, could be something that converts electrical energy into sound. So this is just a generic squiggle here that's used to represent the resistor. And so you might have seen them already in your notice bien. And so it represents something that will consume energy of the circuit, okay? And what happens here is that a voltage is developed across it, and we'll see why in just a moment. Well, when everything is connected together like this, the whole pattern, we get a current. So as long as the conductive wires are properly situated to connect this resistor, we've used pencils before, we'll actually use resistors in the lab coming up, a current is developed, and the current is the flow of electrons. But actually, what's very strange and what's kind of backwards is that conventional current actually flows positive to negative. It flows from the positive side to the negative side. Even though we know the electrons are here, the electrons are on the small plate, and of course the electrons are physically what flow through the circuit to the positive side. So there's this detachment here, this convention from what happens physically. This is how it's considered Ben Franklin got it wrong when he named the positive and the negative. He chose materials that were indeed backwards of what actually happens. They didn't know that it was the negative charge that's the carrier, the electrons are the carrier. They didn't know the atomic model at the time, otherwise they might have chose in different terms. But the convention, as is developed in physics, if you were to take the next course and study the electric field, it's developed with a small positive test charge, and that's just convention. The math works out either way to be the same. The conservation of energy stays the same, so that this circuit still behaves just the same whether or not we have current established from the positive to negative or negative to positive. The only place that I think uses electron flow is the Navy, for whatever reason. Every other place uses this conventional current that goes from positive to negative. So no worries there, it's still going to work. And what we see here is that if current flows through this one little circuit here, this is just a one series connection into the source. It's also parallel to the source, and we'll see kind of why that is. First of all, we see that the total current has to flow through this resistor. Now, if I can name this current, because this is the current through the resistor, I sub R1. So this is IR1, and that's going to flow back to the V source. I see that this is one single loop over here, and so that I total has to be equal to I R1 in this very simple circuit. We'll be looking at more complex circuits later on. And so that the voltage here, the voltage across this R1 is given by Ohm's law. This is Ohm's law written as V equals I times R. So VR1 is I, the current through R1, times the resistance value of R1, whatever that might be. So it produces this voltage over here. What we'll see in a moment is that there is the conservation of energy when we look at not just, well, sort of the current, but also we look at loops, current loops, and in any loop around the circuit, we'll notice that the voltages are going to be consistent. So we'll take a look at that in just a moment. The conservation of energy, of course, comes into play. Here's how it works. For any given loop around a circuit, we can say that the sum of the voltage rises equals the sum of the voltage drops, okay? So technically over here, we've got this little sum of symbol that I'm gonna put in here. So we only have two voltages, so it's pretty easy. But if we were to add up all the voltage rises and the voltage drops, they'd be equal. That comes from the conservation of energy. In this case, the conservation of energy per unit charge, which is voltage. So voltage rise equals voltage drop. What does that mean? Well, it means that if we start over here, and if I start at the negative and go in this, well, clockwise direction, don't confuse it with anything with rotational motion though. We're just gonna choose this as a path, really, to go around the circuit. We start at negative and go to positive, well, that rises. We go from negative to positive, so that's a voltage rise. And over here, we see that this resistor must consume the energy, and so the voltage will drop. It will actually lower because the voltage will be across this element. And we go from positive to negative VR1. So if I go around this one loop, we see that V source rise equals VR1 drop. And that's the conservation of energy. This is consistent for any loop that we can take. So when we look at a series circuit, a parallel circuit, or a series parallel combination circuit, that this law applies. And so it's going to help us analyze the circuit when we see that there's this conservation. What we'll see more so in the parallel circuit, though, is that current is also conserved. The conservation of charge through any junction is equal. You can think of water flowing into a junction. Whatever goes in comes out, but it just may get split up into different parts before recombining. So the water analogy works pretty well when we get to that, and we'll look at it in more detail with the parallel circuit. All right, so this is it for our introduction to the schematic diagram and also how the conservation of energy applies here. Next up in another new video will be analysis of the series circuit, the theory behind it, followed by the analysis of the parallel circuit, followed by analysis of the combination circuit. All right, this is Morad, and out.